Hi, my name is Lucas Dillingham. I'm the sales manager here at BTG Labs. We're a cutting-edge material science-based services and technology company. We work really hard here at BTG Labs to deliver Eureka Moments to our customers. And Eureka Moments are these moments in time where we can deliver new thinking, right? Change minds, change understanding around what we're doing every day. And through that process, solve problems and deliver better product with more reliability and predictability. One way that we deliver Eureka Moments pretty regularly is where we flag seemingly innocuous decisions upstream in the manufacturing process that then have big implications downstream. One particular precision machining manufacturer was having problems coding these precision machine parts. And what BTG Labs did is we interacted with them to provide them with a surface analyst so they could start providing some fast objective data on their material and start monitoring what we call these critical control points in the manufacturing line. One particular engineer took this material and started measuring parts after degreasing. And what she found is that after vapor degreasing, she was not getting the contact angles that really made a whole lot of sense. She was getting fairly middle of the road contact angles, 45 to 55 degrees. And contact angles in this range on aluminum or even on a stainless steel after vapor degreasing processes is pretty atypical. I mean, usually vapor degreasing does an incredibly good job. Usually you get extremely low contact angles and a very, very tight distribution. So understanding that the vapor degreasing process wasn't working the way that she expected it to, she began making some process changes. One of them was changing the solvent out. When she did that, she really didn't see much change. One of them was actually measuring the inside of the degreaser once they'd kind of pumped everything down and got it cleaned out. Realized that she was seeing that the chamber walls were providing a higher contact angle than normal. She then went even farther upstream to the dye penetrant station, where this is a test where they actually check for microcracks in the structure. She found out that at that particular station, the dye penetrant and the technicians in that test station were having a hard time getting the dye penetrant to wet out. Then she started noticing that, hey, wait a minute, there are these blue mats that they've put in the dye penetrant station, and these are new. And she started asking some questions. She said, where'd these come from? And the technician said, well, we got these recently because we wanted a way to put our precision machine metal parts into this bench and not have them scratched up, right? Not have them marred or dented in any way. And she started doing contact angle measurements on these particular mats. And the contact angle measurements she was getting back were 85, 95 degrees, extremely indicative of silicone. She then started measuring kind of inside this hood that exists in the dye penetrant station. She was getting very similar numbers. And when she went and pulled up the ordering information on these mats and basically started to try to root cause this, she discovered that these things had silicone in them. And they were just outgassing silicone in the environment, coating the parts in silicone, dragging that silicone into the vapor degreaser, et cetera, et cetera. I mean, it really had broad implications for the rest of the process. So they were able to remove the mats, try to clean everything up as best they could, and kind of get back to business as usual, right? And so this was pretty interesting for this particular engineer in this group, because when we first started interacting with them as they were collecting surface analyst data, the first reaction was, your system only is reading 50 degrees after vapor degreasing. I mean, vapor degreasing is a great process. We've used it for 40 years. How on earth could that be? Your system's broken. It's not working. And so it took a little bit of work and some coaching and some expertise to have her start measuring upstream in the process until she could find that smoking gun, right? Until she could find that upstream critical control point that was then contaminating the rest of her process. In a similar vein, microelectronics manufacturer developing RF systems and particular boards had ESD mats. And ESD mats are used commonly in microelectronics manufacturing everywhere, right? They're meant to not build up static discharge, or I should say they are set up to not produce a static discharge. You put these components onto a mat to do whatever processing step you're going to do, and you want to make sure they don't get fried. So in this case, a very similar situation where they had ordered a particular brand of ESD mat. All of a sudden, bond failures started occurring at a downstream step, And utilizing the surface analysts, we were able to go upstream in that process with that engineering group to flag the fact that, hey, these ESD mats are outgassing and we're getting silicone all over the boards. We really started doing this by measuring boards right before adhesive application and finding that we were getting about 90-degree contact angles on these materials. And that is a common kind of eureka moment for us, where we go into a particular setup, manufacturing process, and we find that there's a contamination event, and really from something that is super cheap, something that is like in the case of an ESD mat or a kind of soft rubber mat you'd put down for machined components. These are things that people buy every day. They don't think about the fact that these could have impacts on a molecular level. When we talk about designing and controlling a reliable coating process, or reliable bonding process, we get back to controlling those three things, right? Composition of the adhesive or coating, composition of the top 2 to 5 molecular layers of that substrate, and then the application of that adhesive or coating to the substrate. The top 2 to 5 molecular layers of a part are pretty easy to manipulate if you've got silicone floating around in a particular environment. As an example, if I can see a fingerprint on a surface, that's about 1,000 to 10,000 molecules thick, right? Depending on the particular material that's on. So we're talking about a region of the surface that's totally invisible, right? So here we have two completely different applications, two completely different industries, two completely different mats that have different functions, right? One's an ESD mat, one is just a mat, so we've got a soft surface to put a metal part onto. But in both cases, those seemingly small decisions had huge impacts to the business downstream. And through interaction with BTG Labs, surface science experts, we were able to really quickly dive in, solve that problem, and then give them control metrics with the surface analysts that they're able to utilize every day. If you particularly have an active issue that we can help with, check out our website at btglabs.com or give us a call. One of our surface science experts would be happy to talk with you and see what we can do.